Hello, I'm Samantha Kite, and my mentors are Phil Dennison and Michael Campbell. Today, the project is on using the Viewshed and machine learning to model visibility for a terrain and vegetation. Before I continue further into this project, I want to explain what is visibility. Visibility is when you can see up to a certain amount of distance. It is relative to the perspective of one's position along a terrain. It can be calculated using a highly computationally intensive tool called Viewshed. I'll explain what Viewshed is later in this presentation. I want to also dictate what dictates visibility. First thing is the abundance of vegetation. Looking at figure 1, you can see it's a very dense forest with abundance of different vegetation. That vegetation is making it hard for you to see further into the distance. And then in figure 2, there is an abundance of vegetation such as cactus and sagebrush. However, you can see further into the distance due to the arrangement and the height of the vegetation, which leads into the next slide, the arrangement. Arrangement dictates visibility by where the plants are placed and how many are arranged together and what type of plant. In figure 3, there's a tree layer, a shrub layer, an herb layer, and a ground layer. Due to the height of all the different types of vegetation, and the arrangement of the vegetation can obstruct or not obstruct your visibility or how far you can see. Which goes into the next slide, which is height of vegetation. In figure 4, it shows that there can be different heights of trees and shrubs. And of course, as a human, you are under 10 meters. But in that little section of 10 meters, you can see bushes can also obstruct your view depending on how tall the bush is, but also the tree. Another thing to consider is in figure 5, you see the stump and the tip. Well, the stump of, let's say, a pine tree might have a thicker base and the branches go more horizontally out, obstructing your view in a landscape. While, let's say, an aspen, the branches might be higher off the ground and the stump, or the trunk, I should say, is going to be a lot less wide, allowing you to see further. Which moves into the placement you are within the landscape. Looking at figure 6, you are in a desert. As you can see, there is not a lot of vegetation. However, there is different heights or elevations of hills and mesas and canyons. And these can obstruct your vision from how far you can see. There is a hill in front of you, but you can't see what's behind that hill. And that is due to your placement in that landscape. In figure 7, you are at a bottom of a hill and you're looking up in a dense forest. As you can see, there's like smaller trees, there's bigger trees, even though these trees might have thinner branches and, not as many leaves, it is obstructing how far you can see in a distance. And finally, look at figure 8. You're at the top of a hill, and the only vegetation up there what appears to be low height or ground level vegetation, allowing you to see further into the distance. You can actually see quite far. That is also related to the topography of a landscape. There could be lots of hills, or it could be just flat ground. There's lots of hills, you might have a harder time seeing further into the distance compared to if it was just flat ground. Of course, this is not including vegetation, which as we explained, it can affect the visibility. Now that I've explained what dictates visibility, I need to explain relevant background information. Visibility is important for firefighter safety. In the 20th century, fire towers were used to detect fires, and the visibility research was used for fire detection. But now we use technology for fires. This technology has allowed us to have better safety for firefighters. However, this technology can still be improved, and this is why I am wanting to research to further improve the fire safety. And that entails using LiDAR point cloud data. LiDAR, or light detection and ranging, is a remote sensing method that takes measurements of the Earth's surface. It uses a laser, a GPS, and an IMU, or inertial measurement unit. And one point is that you can use LiDAR point cloud data to create 3D models of and maps of the environment. If you look at the figure 10, you can see a plane and its light pulse, or the pulse of the laser, going through the trees. The first detection of the tree is the first return, and that laser will keep going through the tree until it hits the ground. And that is that all those points that were hit from the laser is going to be returned energy and the data that we can use from that measurement. All points have an x, y, and z value, and that z value can be used to estimate the canopy height, which I will explain later why that is important. This is one slide that is a better visual of what is happening when the LiDAR system is taking measurements. As you can see, the plane has the LiDAR pulses, and those dots where the LiDAR returns, where the arrow for LiDAR returns, is the data that we will be using for this project, I should say. Now that I explained to you what visibility is and what LiDAR point cloud data is, I can now go into the goal of this project. The goal is to develop a machine learning model that comprehensively predicts visibility on a pixel-by-pixel basis across large landscapes. This leads into, first, gathering data. I wanted data that was in a desert plain due to the visibility potentially being higher, and to compare it to other data sets that have forests that might be more dense. Once I picked out the location of my data, I then went onto the National Map Government website. I clicked on the LiDAR point cloud data because there's different types of data you can pick from on that website. I put in the coordinates of my plot location, which is in the Escalante region in southern Utah. I wanted a 10 kilometer by 10 kilometer plot, and that resulted in 100 tiles of LiDAR point cloud data. I then downloaded all those tiles. Because those tiles were in the LAS file format, I needed to convert them to the LAS file format. I did this by programming and converting all 100 of these files. After converting them to LAS, I then wanted to create a digital surface model for all 100 of those files. A digital surface model, or DSM, is when a pulse to light or laser from the LiDAR system hits the first return, or the first object or building. It will contain the terrain and object from above ground level. As you can see in figure 12, it is taking points from the surface that it hits first. I also wanted to gather data on the digital train, gather data for the digital train model. After creating all 100 files After creating 100 of the DSM raster data, I then went on to creating a digital train model, or DTM, for all 100 of my files. A DTM is when the pulse light hits the surface of the terrain. Even though it may sound similar to a DSM, it actually doesn't apply to buildings and dense vegetation. It will smooth out those objects to take points along the surface of the terrain. After I calculated the DSM and DTM, I can now calculate the canopy height model, or the CHM. I wanted to create this because I wanted the data in between the DSM and the DTM, as you can see in figure 14. The equation is DSM minus DTM equals CHM. After creating those three rasters, I then went into ArcGIS Pro, a program I use for most of this project, to create 200 random points within the 10 kilometer by 10 kilometer plot. I then went to use a tool called Geodesic Viewshed tool, which is highly computational. And this is where I can calculate my visibility. As you can see in figure 15, a viewshed is where that random point is. It will scan within the data how far or how much what can be seen from that point. Well, what is a viewshed? That's a good question. A viewshed models from a specific point on a plane. It means it can determine how much can be seen from one point. In figure 16, as you see at the top of the picture, you have the seen area and then the not seen area, and those arrows are where your vision, where you can see it within that area. And then below the image, it shows that little arrow pointing upward is the viewer, and then the arrows going out to the corners, to the bottom of the image, show what direction the viewer is viewing. That gives you a better perspective of what viewshed is doing. After calculating those viewshed points, I need to do the following. I first need to create a buffer of 1,000 meters for each points, there are 200 points. I'll be using the buffer tool in ArcGIS Pro. I then will be using all those viewsheds that I calculated to calculate the sum of each point using a tool called zonal statistic tool. After calculating the buffered points and the sum of each point, I need to calculate the area of every point. Those units are going to be meters square. After doing all of that, I can then go into the visibility index. And as you can see on the slide is the sum of each point divided by the area for each point. These are my next steps for this project. I expect to have the visibility index of all the points. I want to calculate the percentage of visibility from each point. I want to use this data to help develop a machine learning model that can predict visibility. And I hope to compare my results to a traditional viewshed model. One thing that isn't the importance of the visibility index is that it can show a percentage of a visible area within a certain radius, and that it allows us to use tools towards all landscapes. By having multiple different types of visibility indexes off of different landscapes, we can create predictor layers which will contribute towards training a machine learning model. Problems that I want to address is the point cloud data is very large. 100 tiles, only 100 files took up 5 gigabytes. That is not all my data, that's just part of it. So it took up a lot of storage on my computer. Another problem is that ArcGIS Pro, the program I used, had problems shutting down and not saving my work. However, once the program updated, I didn't have any more issues from it. Another issue or problem, I should say, that I had is viewsheds are highly computational and require a lot of time to process. A batch, which is doing multiple points at the same time, of course, calculating them separately, it took about 12 hours to complete. And that is it. Thank you for having me.